Hi everyone, my name is Yi Tran. Today I will be presenting my project proposal. The title is Parametric Studies of Metal Additive Manufacturing with Finite Element Analysis. Additive manufacturing, also known as 3D printing, is a process that fabricates a three-dimensional component by joining materials from layer upon layer. In the 1990s, metal additive manufacturing was developed when several companies launched systems for laser sintering that were able to produce components directly. This development enables the fabrication of usable components made in the desired materials in a single-step process. According to Yang and others, they stated that the most well-known metal additive manufacturing process is selective laser melting, in short SLM. Singh and others stated that SLM process uses a fiber laser source as an energy source. This allows a fabricated component to be created when the inserted powder is carried and spread across the build table with the recorder. Robert and others reported that components fabricated from the SLM process tended to be deformed and cracked due to thermal stress by using metal powder. To analyze the deformation of the SML process, Matsumoto and others proposed that a single-layer model could be subjected to a plane stress deformation by combining elastic deformation and heat conduction into a 2D finite element method. Mori proposed a viscoplastic analysis. The viscoplastic analysis would allow simulation of the microscopic deformation in the powder forming process and analyzation of the microscopic of the powder scale. Patil and others proposed a 2D finite element model of the deformed powder surface to predict the temperatures due to involvement of an effective thermal conductivity and a constant density. Shen and others proposed a 3D thermal model to simulate the sintering of two fabricated metal components with different ranges of melting temperatures. The main objective of this project is to perform a parametric study of metal additive manufacturing that would fabricate components and perform mechanical testing to characterize their performance with finite element analysis simulation. A supporting objective of this project is to identify optimal values within the range of selected parameters to minimize distortion. Another supporting objective is to analyze the deformation behavior in the fabricated components made from metal powders, which consist of titanium alloy, stainless steel alloy, and aluminum alloy. Main deliverables for this project are a written protocol that includes the materials, software, and processes necessary to fabricate metal components for finite element analysis, a computer-aided design of a 3D design component for simulation, a documentation of the development of the MATLAB code for any improvements and changes. For this project, the type of metal powder used are Ti6Al4V for titanium alloy, 316L for stainless steel alloy, and 219 for aluminum alloy. Software that will be used are SolidWorks 2019, ANSYS Student 2019 R3, MATLAB R 2019A. The two methods of finite element analysis that will be used for this project is thermal mechanical coupling and element depth and birth technique. The energy density equation will be used to determine the required control of parameters to successfully manufacture a component with the selected laser melting process. Before simulation can be performed with ANSYS, a computer-aided design of a component will be created. The CAD file of the component is then exported to the FBA program for analysis. To analyze the deformation, simulation will be constructed to determine the effects of the laser speed, the effects of the basement temperature, and the effects of the starting laser angle against the z-axis of the 3D printer. A MATLAB code will also be constructed to analyze the resultant displacement magnitude in the area of interest of the FEA model between the different laser speed and the basement plate temperature. Here is the estimated yearly timeline. One evaluation metric that will be used for this project will be the quality surface performance. This performance will evaluate the total numbers of displacement in the component due to different factors. These factors are STL file preparations, material properties, layer thickness, part orientations, scanning parameters, surface angles, finish types, and post-processing. Due to other students having access to the metal 3D printer, time constraint could be a potential obstacle. Fabricated components will have significant time to print. Between work and school, it may be difficult to visit the lab. A contingency plan for this obstacle is to request early access to the metal 3D printer. Another potential obstacle for this project is budget limitations. A contingency plan for this obstacle is to request a budget plan from the committee. Here are the sample MATLAB code and surface plot of the resultant displacement magnitude in the area of interest of the FEA model between the different laser speed and base plate temperature. Resources needed for this project are access to major softwares by February 2020, obtaining metal powders for metal 3D printer by mid-February 2020, and access to metal 3D printer by March 2020. The merits are better understanding of deformation behavior in the fabrication components made from metal powder, distortion minimization, deflection minimization. The impacts are complex and lightweight components, low-cost production, and increased standardization for metal additive manufacturing without deformation and crack due to thermal stress in the selective laser melting process.